and welcome back. Today we're going to be looking at a triangular DL or distributed load again. Only this side, the opposite side, okay, the side with the load, is at point A. We're going to use this as an opportunity to look at 3 different ways of dissecting this problem. The first 2 will start our system at A, and the last one will look at our system from B, and we'll figure out what was the easiest method to use. Let's get started. So today we are going to be looking at this triangular distributed load, and we have already found the reactions. We know what the equivalent load is, we know where it was located, and that's how we found the reactions. If you need a reminder of that, please go back to tutorial 3 on beams, where we find the reactions for a similar load. So before we start finding the internal forces, the one thing that I want to do is find the function for this force. I look what happens in my internal forces when I'm at a distance x, right? So in this case, if I cut anywhere along this beam and go a distance x, I will then get this kind of shape, right? Now I know that the equivalent force is always the area of the shape, and I know that its location is in the centroid. Now for that, I do know that here is 10, I know that this distance here is x, but I need to know what the height here is. And the height here is really the ordinate of the function. So I need to find that first. I can see that it's a linear function, and as it's a linear function, it will look like this. So the function of the load is going to be ax plus b, and I need to know 2 points. And the 2 points that I know really are what happens at point A. Okay, let's call this A and B. At point A, where I have an x of 0 and a height of 10. And what happens at point B, where I have an x of 6 meters and a height of 0. And if I substitute these 2 things, I can find out what the load function is. So let's start with the first one. So if I substitute x equals 0 here, ax obviously falls off, so I get b, and I know that that needs to equal 10. So b equals 10. I'm now going to look at my second equation, okay, so using point B, and here I know that when x equals 6, I know that I have a times 6 plus b is 10, we established that, and I know that that needs to equal 0. So 6a equals minus 10, and therefore a equals minus 10 divided by 6, which I can write as minus 1 and 2/3. And therefore wx, the function of the load, is going to be minus 1 and 2/3 x plus 10. Now that we've established the load function, we'll use it for the first 2 of the 3 methods that I'm going to show you. In both the first 2 methods, the cut is going to be the same. Let's look at the cut together and then decide how to proceed next. Now for both of the first methods, we're going to start off with the same cut. Okay, so I'm just drawing this out here. So for this cut, I have an x that starts from here. I've got a reaction force of 20 kilonewtons, and I've got part of the force, which will look something like this. And here for completion, I've got my axial load, which I'm not going to touch on today. I've got my shear force, and I've got my bending moment. For this first method, I'm going to be looking at the trapezoid shape, and I'm assuming that I either know these things off by heart, or I have a book readily available which lets me know what the area and where the centroid is of this shape. So what do I know? I know that this here is x. I know that I've got 10 for the height here. The height here is h2. Okay, this is h1, in case you're looking in a book. And what I can find is, I can find that the equivalent force, okay, which I know is the area equals half of x times h1 plus h2. In our case, that means x over 2 times 10 plus this equation that I found before, so minus 5/3 of x plus 10, and I can write that out as x over 2 times minus 5/3 x plus 20. I can further simplify this to minus 5x squared over 6 plus 10x. And that essentially, that area is essentially the equivalent force. Now I need to know where to put this. Okay, so what is xc? Where is the centroid of this? And the equation for the centroid of a trapezoid is x over 3 times h1 plus 2h2 divided by h1 plus h2. Okay, and that essentially gives me x over 3 times 10 plus 2 times my equation minus 5/3 x plus 10 over 10 plus the equation of minus 5/3 x plus 10. And I can write that out slightly more neatly as x over 3 times 30 minus 5/3 x over 20 minus 5/3 of x. Let's start off by looking at the shear. Okay, so to do that, I'm going to do sum of forces in y equals 0. So I've got 20, then I've got this equivalent force, right? So minus 5/6 of x squared plus 10x. And then I've also got minus the shear force. So the shear force in this case is going to be 20 minus 10x and plus 5/6 of x squared. And let's figure out a few interesting points that we might want to check. What happens when x equals 0? What happens when x equals 6 meters? So that's point A and point B. So when x equals 0, I get 20 kilonewtons, which is exactly what I'm expecting, right? That is the reaction force at point A, so that's great. What happens when x equals 6? Well, then I've got 20 minus 10 times 6, so that's 60, and plus 5/6 times 6 squared, so that's 36. And that works out as minus 10 kilonewtons, which is exactly what I'm looking for on the other side. So I've got 20 here, and I've got minus 10 here. And how does it look in between them? So the first thing I know, it's not going to be a straight line, is it? Because I can see that this is definitely parabolic. It's parabolic to x squared. So I know that it's going to look parabolic. What I can do is I can add maybe another point, say in the middle. What happens when x equals 3? So I got 20 minus 30 and plus 5/6 times 3 squared, so that's 9, and that works out as minus 2.5 kilonewtons. Okay, so when I come to the middle, I'm going to be somewhere here at minus 2.5. Okay, and my parabola is going to look like this. Okay, and just to note, this is a parabola. What I'm interested is finding out where do I cross at 0? So what is that distance there? I know to cross at 0, I know the shear force has to equal 0. So let us take our equation, 20 minus 10x plus 5x squared over 6. This needs to equal 0. We can solve this using this equation that you probably remember from before, where we've got minus b plus minus a square root of b squared minus 4ac over 2a. In our case, a, b, c. So we've got minus 10, so we've got plus 10 here, plus minus 10 squared, so that is 100, minus 4 times 5 over 6 times 20, square root of that, and all that divided by 2 times 5 over 6. And if you solve that, you get plus 10 plus minus 5.77 divided by 10 over 6. And so mathematically, we get two answers from this. One of them is 2.54 meters, and the other one is 9.46 meters. Now, we can see that although these two are valid answers mathematically, only one of them works physically, right? Because this is within the beam, this 9.56 meters is out with the beam. So that is not a valid answer here. And we can just write 2.54 meters here as this point of 0, which is going to be very important for us doing the moments. Okay, let's move on to finding the moment. So to do that, we want to sum the moments around the cut, with this being my positive direction, counterclockwise, and I'm going to start off with the 20. So I've got minus 20 times x. Then I've got this trapezoid complicated load. It gives me a positive moment though, so that's plus the equivalent load, so that is minus 5 over 6 x squared plus 10x. And then I need to times it by the centroid. Now just a reminder, the centroid as it appeared in my book, which was here, gave me this distance here. But for the moment, I'm going to need the other distance. So actually what I'm going to need is x minus xc. So let's write that in. I've got x minus this whole thing, x over 3 times 30 minus 10 over 3x divided by 20 minus 5 over 3x. Close those brackets and then close those brackets, and plus the moment, and all that equals 0. All that is in equilibrium. I'm going to write this out. I'm not going to write it out too organized because I'm just going to substitute values. So I get 20x and then minus this whole thing. And so let's see what happens when x equals 0, what happens when x equals 6, so that's point A, point B, and what happens when x equals 2.54. That is obviously an interesting point for me because I know that when the shear crosses 0, I'm going to get either max or min moment. So when x equals 0, it's pretty easy to see that everything works out as 0. When x equals 6, that gives me 120 here, and then I've got minus, that works out as 30, and this thing here will work out as 6 minus 6 over 3, so 2, and then times what is in these brackets, that will work out as 10 over 10. So here I've got 4. So 120 minus 30 times 4 gives me 0. Another indication that I'm on the right path, because at the two ends of this simply supported beam I have a moment of 0, which is good. And then the last thing I need to put in is that 2.54, and that works out as 50.8 minus 20 times 2.54 minus 0.84 times 21.53 over 15.76, and that works out as 50.8 minus 27.83, and that works out as 22.96 kilonewton meter. And now finally I can draw on that bit here. So I've got here 22.96 kilonewton meter, and my parabola is going to look something like that. And just a reminder, this is also a parabola, x to the power of 3. This one was x to the power of 2. And that is us finished the first method. Now, the second method is really just a simplification or overcomplication, depending how you see it, of the first method. This is really helpful for when you don't remember what the centroid of a trapezoid is, and building on the fact that in engineering, most of the things we deal with are going to be triangular or rectangular forces. So in this case, I'm just going to divide that same load into a rectangle and a triangle. Let's see how that goes. So looking here at my forces, you can see that I've just divided this into two shapes. And the reason that I've done it is really because I find it really easy to remember that the centroid of a rectangle is in the middle and the centroid of a triangle is 1/3 and 2/3 from the opposite side. And that just makes it slightly easier to remember. Obviously, if you remember the trapezoid, good on you. Let's do it this way quickly to validate the results that we've already received. So starting off with the shear, sum of forces in the y direction equals 0, and I've got my 20 going up, then I've got the rectangle going down. And the only thing I do need for this is I do need the height, h2, which really equals my function that I already found. So for my rectangle, I'm going to have a height of minus 5/3 of x plus 10. That's going to be my height, and times x, right? This same x here, like before. And then I've got to add on my triangle. So this was my rectangle. Again, it is negative, so minus. And this time I need 10 minus that height. So I've got 10 minus this thing, minus 5 over 3x plus 10. That gives me my height times x and over 2. And that gives me the area of the triangle. And then obviously I've also got my minus s of x. And all that sums up to 0. So the shear force equals 20 minus this thing, which I can just write out as plus 5 over 3x minus 10. Just introduce the minus within the brackets times x, and then minus this thing here. So minus 10 minus 5 over 3x plus 10, all that over 2, and multiplied by x. Let's check the points that we have here. So we're doing this as a check. What happens when x equals 0? What happens when x equals 6? So point A, point B. And what happens when we have what we're expecting to be 0, 2.54 meters. Okay, at 0, the second bit comes off, the third bit comes off. I'm left with 20. That's great. When I have 6, I've got 20 plus, that works as 10 minus 10 times 6, that gives me 0. And then I've got this thing here. Third bracket works out as minus 30, and that gives me minus 10 kilonewtons. So this worked out, this worked out. Let's do this last check. So I've got 20, this thing here, which is minus 14.64. And then I've got this last bit here, and that works out as minus 5.376. And so that is 20 minus 20, and so I get 0. So once again, that works out well. Let's now move on to the moments at the cut. Okay, so I've got my moment first of all, so mx. Then I've got my negative moment from my reaction force, so minus 20 times x. Then I have got a positive moment from that rectangle, so that is plus, as we said before, the height is that function that we found, so minus 5 over 3x plus 10, that's the height, times x. That gives me the force once again, and if you'd copied that over from the previous one, that's exactly the same thing. And then we have to multiply by the centroid, which is going to be times x over 2. And then we've got our positive moment from the triangle, which once again, like before, the height of that triangle here, that is 10 minus wx. So in our case, 10 minus 5/3 x plus 10. That gives me the height times x over 2. That gives me the area of the triangle. And I need to multiply here by the distance from the centroid. And in this case, it is pretty simple because it's just the centroid of a triangle. So I know that it's 2/3 of x. Okay, so both of these, this one here, that is the distance, and that here is the distance. And all of this needs to equal to 0 because we're in equilibrium. So the moment equals 20x minus this thing here, so 5/3 x plus 10 times x squared over 2, and minus this next bit here, 10 minus 5/3 x plus 10, and over, let's see, 2 goes, 3, and here we have x squared. Okay, and this bit here, that is from our rectangle, and this bit here is from our triangle. And now, just like before, let's see what happens at our points of interest. So what happens when x equals 0, when x equals 6, okay, point A, point B, and what happens when x equals 2.54. So expecting to get 0, 0, and 22.96. And so if we check 0, we can see that all the terms add up to 0, so that is 0 here. If x equals 6, we get 120 here, and then minus, within the brackets we get 0, so that is 0 here for that rectangle bit. And then for this bit we get 120, and that gives us 0. And for this bit here, if we calculate, we get 50.8 minus 18.6 and minus 9.1, and that works out as 23. So probably just depends on how many points I took after the decimal place, but this is close enough, so I'm happy with that. And that is method number 2. And for the very last way, I'm just going to consider perhaps it's easier starting from the other side. So I'm going to ditch the direction of the cut that I've done and just look for the simplest way to do it. As long as I'm consistent with my sign convention, this will all work out fine in the end. So let's look at that last method. So as I mentioned before, for this method, I'm actually going to look from the other side. So if this is my bit of beam, I'm going to start looking at x from here, which means that now I need to consider the reaction on the other side. So it's the 10 here. And my force is going to always look like this. It's going to be triangular. Okay, so none of this pesky trapezoid or having to divide it. And the only thing I need to be quite consistent is that these are internal forces. So they need to be equal in value, but opposing in direction to the internal forces from the other side, right? Because these are all internal. So the minute I close everything up, they have to disappear. So before I look at the forces, the only thing I'm really missing is I need to find the height here, which is also the function of this load at any given x. I have these 2 points, right? So here I have 0, 0, and here I have 6 and 10. Just remember that I'm going in this way with my x, okay? So if I substitute my 2 points, I find out that the function for the load, which is also y, the height of my triangle equals 5/3 of x. I just do need to remember, and I'm going to emphasize this again, that x now starts from here. So if I move on to calculate my shear, I've got Sx going up, I've got 10 going up, and I've got minus this equivalent load of the triangle, which is the height, so 5/3 of x, and times x over 2. That gives me the area of the triangle. And that equals 0. So S equals 5x squared over 6 minus 10. Now let's see what happens when x equals 0, when x equals 6, and when x equals, now for this one I need 6 minus 2.54 because I'm starting from the other side. So this one is going to be 3.46. When x equals 0, I can see that I get minus 10. That's perfect. That's exactly what I'm expecting. When I'm at 6, which means this is obviously point B, this is point A. When I'm at 6, I get 20 kilonewtons. And when x equals 3.46, I get 0. So all in all, working from the other side seems much simpler this time round. Let's move on to finding the moment. So if I do the moment at the cut, I've got my moment, which is negative. Then I've got a positive reaction force, so plus 10 times x. And then I've got a negative moment from this triangular force, which is, as we said, the area is 5/3 times x over 2. That gives me the area, which is the force. And it's always going to be placed, right, at a distance of the centroid. So this is going to be the distance my equivalent force is, and that is going to be 1/3 of x. So I have here times x over 3. So this is the force, and this here is the distance. And that equals 0, and I can write out this equation as mx equals 10x minus 5x cubed over 18. And once again, I want to see what happens when x equals 0, what happens when x equals 6. So this is point B, this is point A, and then what happens at the max when x equals 3.46. Let's see if these match up. So when x equals 0, this whole thing zeroes out. That's fine. When x equals 6, I've got 60 minus 60, and that equals 0. So yay and yay. And let's do this last one. What happens when x equals 3.46? I'm expecting that max min result. So I've got 34.6 and minus 11.51, and I get 23 kilonewton meters. And I'm happy with that. So we've had a look at 3 different ways of calculating the internal forces when we have a triangular DL. 2 of them started from one side and were perhaps a bit more complicated, one taking a more complicated shape into account, 2 simplifying it into 2 simpler shapes but still 2 shapes, and one which I think is the simplest just included us changing our coordinate system, looking from another direction and being consistent and getting the same answers, which was much more simple in my point of view. So I hope you've learned something new, and I hope you join me again to look at some more trusses, beams and structural engineering. Bye for now.